Nice. So I just want to like inform you guys or ask you a little bit about like the midterms. So are they next week for the rest of the courses, or when are your midterms in general?
So usually, actually, this is the only course that is like not a block course. It's like for the whole,
Semester.
yeah, for the whole semester. So I mean, usually we have them like seventh, eighth, ninth week. So like each professor decides separately.
Okay, so for example, if we choose next week, will that be like a time that you guys are occupied, or will it be like a good time for you?
I think it will be a good time.
Yeah, I think so too. Yeah, between like the different blocks, so you have nothing hopefully that would occupy you.
Mm-hmm.
Okay, that's nice. So most likely I'll just confirm with Batul, but most likely next week you will have your midterm. And I will also today launch the what's it called? The project idea submission thing. It's very simple. All you have to do is just build a GitHub repo with a beautiful README that describes what your idea is, where the source data set that you're going to use is located in, and basically a couple of the steps of what algorithm you would like to choose or what algorithms you would like to compare between and things like that. That's it. Is everybody like started thinking about their ideas? That's a no.
No, so some of us actually started.
That's nice. That's good news. So for today's lecture, it's gonna be almost similar to the edge detection lecture, but instead we're going to be focusing on corners now. That's kind of like the main difference between that lecture and this one. So before we go like deeper into the algorithms and understand those things, we would like to understand why, or the reasoning for why we want to do that. So for example, you take these two images, right, of clearly the same location, and we would like just to combine them to build a more like panoramic, bigger picture. In order to do that, you could spend like the rest of like what you could do is you just set the transparency of this one a little bit low, set the transparency of this one a little bit hard, and then try to like put them on top of each other and see when there is a big match, right? So that's what we could do. And that's similar to like, that's something that you would do with your hands, but we could define exactly the same thing or a similar thing using an algorithm, right? So that's the point is to build an algorithm for it. So the algorithm would be something like detecting interest points or places where the image is like most unique. And then these are like called the features in both of these images. And here we could see clearly that these and these are extremely similar, and these might be the places that we would use to judge, right? And as a human being previously, sorry, here, we could clearly see that these are like the two places that are in common between these two images, right? So what we will be doing is we will extract the vector feature descriptor surrounding each interesting point. So these all of these are like interesting points, and they will have a feature descriptor. So the feature descriptor is just there to like verify, instead of like having to use the exact pixel values for that neighborhood. So in cases of like, I don't know, changes in illumination or stuff like that, we might be able to still get a feature that is similar in here and in here without the pixels having to be a 100% match. Once we do that, we determine the correspondence between the descriptors and the two views. And as we said before, so these points are similar to this location, and these points are similar to this location. And that makes it very easy to just put them on top of each other using some sort of an algorithm. As you can see, it was not just putting them on top of each other, but it required a little bit of rotations and scaling and stretching of the image to make sure that the landscape is as similar as possible to this one, right? So they're in the same size, same scale, same everything. And this technique is not just useful for merging two images, but we could also check it out. I'm not sure if you guys can hear my video audio, but let's try it. Opa. Can you see this?
Hi, I'm Helena Lenikova. I'm a
Yes, we
student
can
at Mullen
hear.
College of Engineering, and this summer I worked on improving Visual SLAM and integrating it with ROS. Visual SLAM allows the robot to map out a new environment and localize itself within that environment using only camera images. Visual SLAM works by tracking image features between camera frames and using them to determine the robot's pose and position of those features in the world. The system also provides an estimate of the position of the robot in the world coordinate frame, shown with the green markers, compared to the combined odometry estimates from the wheel encoders and IMU, shown in yellow. The system also allows us to reconstruct a 3D point cloud of the environment, which could be used for creating 3D models of objects or larger scale environments like buildings, such as this reconstruction of Willow Garage. Visual SLAM allows a robot to have another source of odometry estimates, to localize itself within a new environment, and reconstruct 3D information about its surroundings, all from camera images. All this software is available for free and open source as part of the vSLAM stack at ros.org.
So like small question, did you guys understand what vSLAM is, or like did it interest anybody? Yeah, especially for the robotics guys. So if you would like, for example, to work on this as a project, that would be amazing. So just combining basically like Visual SLAM with the Kalman filter, which is also like a state estimator and like a hidden state estimator. That would be like a very beautiful idea that could, I'm not sure if it's already implemented. I'm supposing that it's already implemented, since both of these algorithms are very similar, but one works on like the visual side and the other one works on the hidden state side. But I think it would benefit drastically from that combination. Does anybody know if this combination already exists? Let's check. vSLAM with Kalman filter. Okay, yeah. Yeah, it already exists, I think. Yeah. I think it's still a good idea. Well, since it exists, so it's a good idea. Let's continue the lecture then. Right, so vSLAM is a pretty cool technique. I quite like it. So if anybody wants to work on it, that would be amazing for your projects. Now let's go to the feature detector as we were speaking before. So right now we will see two types of feature detectors. The first one is the hairs detector, and then we will speak about SIFT, which is like a better version of the hairs detector. That is, the way we will describe it is not similar, but we will see an extension of it that is quite similar. So what makes a good feature, right? Or what makes a good place, like an interest point, something that we could use to compare between different images. Previously, we were interested in segmentation and we were interested in understanding the objects, right? So we were interested in finding out the corner or the edges of not the corners. Yeah. So we were interested in detecting the edges or like the boundaries of that object. But now we're interested in finding the best or most interesting points in an image. So we have three options, right? So we either have like an image or a point like in here where there's no change happening, or a point on the edge, which is at least like there is a change in one direction. And then there is a point which is on the corner where you have a lot of changes in multiple directions, right? So you probably have guessed already from what I've been saying, that the best points or the most useful, interesting points that we could use are those who are at the corners of the objects, right? So the corners of the objects are like places where the description can be at like the highest potential. Okay, so exactly that, right? So this no change at all in any direction, no change along at least one of these two directions. And then here, when it comes to a corner, we have a significant change in all of the directions. So Harris corner detection algorithm is based on corners, as his name suggests. Yep. So here, for example, this is an example of what the Harris corner detector would try to detect. So it would aim for detecting places exactly like this. And if we look at it in here, it does detect the shape overall of the object, but does not focus too much at, for example, the edges in here, right? It only focuses on places where there is major change. For example, as you can see in here, just like what is this? 90-degree angle between black and white, right? So here the same, and it shows you the most interesting places inside that image, right? So it's not about detecting the shape of the object. It's not about detecting the edges or the boundary of the object. It's about detecting places in the image which could contain or which are likely to contain important information about that image. So the mathematics behind Harris corner detector are quite easy, right? So what we want to do is to find the place inside the image where there is a major change happening by sliding a small window, right? So we take a window in here, for example, this is the original window, the blue one in here. And if we change that window just a little bit, we what is it called? We slide that window a little bit in any direction around it, right? So for example, you slide it by 6 or 10 pixels and you calculate the difference. If that difference is very drastic, very big, that means it's a corner. If it's not very big, that means it's not a corner. So exactly in here, for example, right? So here, if you change it in any direction, if you move in any direction, just a little bit, the pixel values, when you like do the difference between the pixel values, they're exactly the same. But here, what I'm supposing is that this is like the object. Most likely between this and this, there is like a difference in color, right? So let's say that this one is a little bit like that. And this one is red. So when you move this side, right, when you move it a little bit to this direction, you're gonna see some changes happening here. Like the pixel values between this and that will be different. And here, when you do any like movement in any direction, you are also going to see some changes happening to the pixel values. And how do we define this, like these changes? Simply by saying like the sum over like x and y belonging to this w. This is like u and v are what are they called, are already defined, right? So they're already set. Let's say 10 and minus 10, for example. And we're gonna have to do this for a lot of the u and v's, right? So, but if we have already just one u and v, and we have just one center in here, then it becomes quite easy, right? So it's the identity of, or like the image of x plus u, y plus v minus the I of x, y squared. So it's kind of like the MSE between these two different images. The one problem is that it's quite difficult to compute this for all window sizes or for multiple window sizes, for multiple u and v's in different direction and different scales, and of course for all the for like each and every single pixel in that image. So here you have like 3 different variables that are like changing. If you include x and y, then it becomes like 6 different variables that are changing. And now you're like speaking in numbers that are, or like complexities that are just impossible to compute for like an algorithm that could be useful. So how do we simplify that a little bit is by simply saying that the image value, or yeah, the image value at x plus u and y plus v is equal to the image value at xy plus like a certain derivation of it. So basically, if we consider that the u and v are just equal to, let's say, 1, and we're using Sobel's filter to compute what are they called, the derivatives. So you can have this function pretty much simply said that the I of x plus u at y plus v is equal to I x y plus a certain derivative of x and a certain derivative in this direction of y, but you know, u and v are just 1. But the higher that u and v get, or the bigger the u and v get, the more the higher order terms we would like to include in order to be, you know, more accurate. Or you would need to use a bigger Sobel filter to do that, right? So if the motion uv is small, then the first order approximation is good enough for us, and we could use it. Again, a change like this is not small enough, right? So this is not something that is small. This is quite big, right? So you can see in here, this is like at least 20 pixels. So that's not something that the first order approximation is good for. But if we're speaking in terms of like 2 to 5 to like, I don't know, 6 pixels, then it's definitely going to be at least a little bit accurate. Just for the sake of like simplifying a little bit the math, instead of saying the derivative of I with regard to x, we're just going to say I of x, right? So that's just to simplify a little bit the math. So if we bring this back again to the Harris corner detector math again, we get the following, right? So I of x, y plus I of x in the direction of u. So this is the derivative again in the direction of x, plus I y of multiplied by v minus xy. And that gives us, this goes away, this goes away. And that gives us ixu plus iyv is equal to, squared. And that gives us the simple formula like this, right? So it becomes a plus b squared, which is who knows this beautiful function? Is that so?
Yeah.
Nice. So if I tell you I have the sum of a plus b, this is like this. Is it equal to the sum of a plus the sum of b?
Yes, why not?
Nice. So imagine that you have like 2 arrays, very simple, as if you're doing some programming. You have 2 arrays, and you're going like the index I is going through each one of them and just summing individual values together. And then it just gives you the total sum of the 2 arrays. You could do this simply by summing the first array alone, summing the second array alone, and then summing them together. So this is also very basic. Combine these 2 mathematical like techniques and you get the following for this one, right? So what do you get is, let me write it here. I squared, I'm just going to make it simple, right? I squared plus 2, ix, let's write it, right? Ix u squared plus 2 of ix u times I y v plus I y v squared. So this is what we get. Now we introduce the sum into each and individual value. So that gives us, the sum of this alone. And then the 2 also is independent, so we just put it outside. And then we have the sum of the first one alone. And that simplifies a little bit the formula. So here, when we come to this place, what do we get is the following, right? So this is like the simplification that we were just seeing. Sorry. So ixy plus u plus iyv squared is equal to a u squared plus 2b uv plus cv2 squared, where the a is equal to the sum of x over xy belonging to the window w of ix squared, where b is equal to the again the sum of ix multiplied by iy, and c is equal to the sum of iy squared. So this is exactly what we've been just writing, but we have split the sum between each one of them. So we introduced the sum inside, and we took away, because so basically the u squared and the v and u and v squared are not dependent on the sum. They are already fixed in here, so they're not dependent on the sum. So they could be like taken out of the sum simply like the 2, right? So for example, here the 2, we took it outside of the sum. That's also pretty easy to do. And here we just define these 3 values, and it should be quite easy to calculate them, right? So the sum of I squared, this is just the derivative in the direction of x. You just sum its squares. Simple, right? So it's a basic function. Here, this is the derivative in the direction y. You just, again, sum its squares. How do you calculate the I of y and I of x? Again, we've seen multiple filters that can do exactly this. So it's not something that is very difficult to do. And here we have the multiplication of I of x and I of y, and then we just sum them over. And that, again, is something that we can easily do with a Sobel filter, right? Before we go a little bit deeper, we will have to speak a little bit about eigenvalues and eigenvectors, but we're not going to go into so much details. I'm supposing that you have done PCA with Professor Khan, right?
Yes.
Nice. So this math is going to be extremely simple for you. So the mathematics behind like the Harris corner detector would look like this. So it's approximated to the first order approximation like that. A of u squared plus 2b uv plus cv squared. This is the basically, what is it called? The square of like a matrix with a vector, and it's written like this, right? So the vector form of this equation would look something like this one. And if you simplify it, you will get exactly this beautiful function here. What we will have, since uv is a vector that is already defined for us, so we said it's just a small value that we will define. We have this as fixed. It's the A, B, B, and C that we will need to calculate. The H matrix, remember, H is very simple. It's just a couple of filters, and then we do some sum over them or some multiplications between them. This equation is the ellipse equation. It's very similar to the PCA equation that you guys have seen, right? So for example, if you have data like this is your data. What PCA does is, instead of using this, what is it called, space, it will try to create a space in here. Sorry, let me use a different color. Yep, it will try to create a new space in here, where one axis maximizes all of the variance, and the other axis takes as the least amount of the variance possible. If we look at it in this direction, the variance in this is like that, and the variance in this direction is like this. So they're both quite, minimal. But if we look at it in this new feature space, we have this variance is equal to something that is very high. So it contains the most information about the image. And this variance is very low. And these give you, of course, the components for the 2 components for the principal component analysis. So before we go a little bit deeper, we have to understand again what are just a little bit what are they called, the eigenvalues and how to calculate them. But overall, so you guys are already familiar, if we have a matrix H, calculating its eigenvalues will reveal to us what is the amount of intensity change in each different direction, right? So here and here. Review eigenvalues. Say that you have like a, what is it called? You're trying to, you have a matrix and you want to calculate its eigenvalues. Very simple way to do this is by saying A of X is equal to lambda of X, and then you just calculate the eigenvalues by calculating the determinant of A minus lambda I is equal to 0, and then finding the eigenvector corresponding for each individual eigenvalue simply by multiplying A minus lambda of I times X is equal to 0. So for example, this is our A. It's a 3x3 matrix, already too complicated for us. We only need like 2x2 matrices, maximum 4x4 or 5x5. The eigenvalues for this one will be lambda 1 is equal to 7, lambda 2 is equal to 3, and lambda 3 is equal to -1. You plug them into this equation and it gives you the following eigenvectors. How do we find the eigenvalues again? We do this, the determinant of A minus lambda I is equal to 0. The determinant of this minus lambda of this is equal to 0. This again puts or goes into the, what is it called? Inside, right? So you have -1 minus lambda, then you have 3 minus lambda, and then you have 7 minus lambda is equal to 0. Sorry, the determinant of this one is quite simple. So it's -1 minus lambda times 3 minus lambda times 7 minus lambda minus 0 is equal to 0. And then you have everything in here multiplied is equal to 0. This is just a simple function. So it's if 3 values are like multiplied and they give you 0, setting at any one of them to 0 would set the all multiplication to 0. There are no values that might like break this function, for example, divided by something, or you can't be like afraid or worried that some of these values might give us some problems. So what happens is if lambda is equal to -1, you get -1 minus -1, which is +1. So this becomes 0. 0 multiplied by anything. Of course, we don't worry about whatever is here. Nothing is undefined or something. So everything is becoming to 0. If lambda is equal to 3, then this part is equal to 0. So it's again a eigenvalue. If 7 is multiplied by, if lambda is equal to 7, so 7 minus 7 is equal to 0. Multiply everything, that gives you 0. So these are like the eigenvalues. How do you get the eigenvectors from your eigenvalues? Say that we take, for example, lambda is equal to -1. You put lambda in here and you simply calculate this beautiful function. And what does that give you? Is A plus lambda of I times X. You do the math in here. So this gives you a 0 in here. This gives you a 4. And this gives you an 8. You do the multiplication and there you go. You get your beautiful eigenvector. So we have just seen, of course, you have to do exactly the same thing for lambda is equal to 7 and lambda is equal to 3, but the math is quite simple and everything should solve itself in the end. So hopefully, once you have done that, you would get this new these new eigenvectors or eigenvalues, and they will give you one direction in which the change is the fastest and one direction in which the change is the slowest. Or in terms of like the PCA words, you would get one direction in which the variance is most captured and one direction in which the variance is least captured, right? And here what we can get, so you can visualize basically the H matrix, which is an ellipse with axis lengths determined by the eigenvectors, and the orientation is determined by the the length is determined by the eigenvalues, and the orientation is determined by the eigenvectors. And lambda 1 and lambda 2 are the eigenvalues for that H. So here, this gives us like a small definition. When you have very small change, right? So when you have very small eigenvalues, this means both directions have very small change in them, this means the region is flat, right? So the region does not have any changes happening into it. And that puts us back into this example, right? So into the first example where we made the change, but there's nothing changing between the two different locations. The other cases are one edge or one eigenvalue is much bigger than the other edge, right? So that would tell us that, for example, if lambda 2 is bigger than lambda 1, then the eigenvector 2 is much bigger than the eigenvector 1, and that's a, what is it called? A edge in this horizontal direction or vertical direction, depends which one are you using. And then in the other case, again, where lambda 1 is much bigger than lambda 2, again, it's an edge in the direction of lambda 1. Whereas the thing that we want the most is the corner, right? In which both of them are extremely large, but both of them are like similar to each other, right? So if it's like a corner, then it should be like a 90-degree corner, then they should be quite similar to each other. It increases in all directions. So this is an example of what the Harris corner detector does. It takes an image like this, and again, it finds all the points that might be interesting. So far, we're not really doing the matching. We're not trying to merge two pictures together or merge a map of the 3D world together. All we're trying to do is find the points that are interesting inside the image, right? So this gives us like the corner response, or the whether it's a high point or high feature place, or it's a low interest place. So we can see here, for example, the background is being completely ignored because it's quite stable. But if the background contained like a lot of changes, then the Harris corner response detector would have like a lot of red in the background here. But here we can see these are like the most interesting points in it. We're not really focusing on the edges. You see, the edges are being ignored. We're focusing on the object itself and the features in it that are very interesting. Once we get that, we try to threshold the corner response to a certain level. So we're not going to be just very noisy to small changes in the data or in the pixel intensities, but we're only going to look at the big changes, right? And after that, we do some non-maximal suppression, because as you can see in here, all of these are probably representing the same pixel, right? So we don't need all of these pixels in here. We just need one of them, right? So non-maximal suppression would just go into each one of these places, and instead of representing them by 500 pixels that are just mushed together, we just represent them with one pixel, and that simplifies things a little bit. So these are like the Harris features that we have detected. And these allow us to detect corners in the image or detect features that are very interesting inside the image, where the change is maximum. In practice, we don't just include or not include basically the changes. What we could do is we weight each derivative value based on its distance from the center of the pixels. So previously we were doing like this, right? So the W of xy was plus 1 inside the window. So if you're looking at a window of size like 5 by 5, then you would only consider the values inside those 5 by 5 pixels. Everything else will not be influencing the H matrix. Whereas for the Gaussian way of determining things, basically inside that matrix, you will still have the highest contribution, but outside of it, those pixels that are on the borders of that window will still get some contribution to your H matrix, just to give you more understanding of what's happening around you, right? So just to summarize again the steps for the Harris corner detector, first, you just compute the X and Y derivatives of an image. Second, you compute products of derivatives at each pixel, which is this part, IY, IX multiplication. Compute the sums of products of the derivatives at each pixels. So you have this sum of IY and IX. Define the matrix H. which is this, right? So it's I of x squared, I of y squared, and the multiplication of each different derivative. Compute the response of the detector at each pixel. So the response is basically this one, right? Oh, sorry, we didn't talk about the response. Yeah. So the response is basically a combination of the lambda 1 and lambda 2, right? So if lambda 1 and lambda 2 are high, the response are high. If they're not high, then the response is not high. So sorry for not covering this one. I did not see the slide, but the response is simply determined by this function. This function is quite simple. So this function gives you the following: lambda 1 times lambda 2. This is a very big number in case of like, if both of these values are very high, minus alpha times lambda 1 plus lambda 2 squared. So what does this give you, right? Let's try to plug into this function two very small values, or one small value. Let's put one small value. So if we put one value is equal to 0.1 and the other value is equal to 10, let's see what happens here. So 0.1 times 10, this gives you 1, minus alpha 0.1 plus 10 is equal to 11. 11 times 11, this gives you 120 something. 120 something multiplied by, I don't know, 0.05. That gives us, I don't know, let's say it gives us 5. So 1 minus 5, this is a very negative number, so it's not something that we want to get, but this is an edge because one of them is very, very big compared to the other one. Now let's try again, but with two small values. So 0.1 and 0.1. This gives us 0.1 times 0.1, which is 0.01, minus, let's say 0.1 plus 0.1 to the power squared. So this is like very, very small number. Let's say 0.00001. And the difference is going to be, let's say 0.01, something similar, right? So the values will be very, very small values. So this is a flat region, something that we don't want. This is where the response is very low. Now, if we want a response that is very high, basically we would need the following: an R that is very big, meaning we have a lambda 1 that is, let's say 10, and a lambda 2 that is also 10. 10 times 10, it's 100, minus 10 plus 10 squared, which is 400, but multiplied by this alpha, which is 0.05. 400 multiplied by 0.05, it's like 4 times 5, which is 20. And that gives us 80. So 80 is a large positive number, and that gives us a corner. So this is the response matrix, and this is how we we measure the response for what is it called, for the Harris corner detector. This is just one way of defining basically or combining lambda 1 and lambda 2 in a single value that can tell us if it's a corner or not. There are other techniques or other R functions that could do exactly the same thing, and they're a little bit simpler, but this is just a way to define basically, or to compute exactly that. So we go back here, so we compute the XY derivatives, compute the products, compute the sum, define the matrix H at each pixel, and then we compute the response at each pixel. So we compute R at each pixel, threshold on the value of R, and then we compute the non-maximum expression. For each pixel that meets the criteria in SEX, compute a feature descriptor, which we will speak about a little bit later. So the feature descriptor is quite simple. It's very similar to what we have seen previously in HOG, but now it's not like for the whole image. Now it's just for like the small region of the image. So the Harris Corner detector is rotation invariant, meaning if this corner is like, for this corner we have this, and for this corner we have this, but the eigenvectors will change. but the eigenvalues will stay the same because the eigenvalues are just the length of these, what are they called? Of these eigenvectors, but they're not going to change. Intensity changes, it's partially invariance for intensity changes. So for example, if you just push it a little bit higher, it is still going to detect the majority of this. Since it works only on the derivatives, it should be invariant a little bit to the intensities of I is equal to I plus B. But if we're working on like scaling intensities, so I is equal to A of I, then here we could have some issues with the thresholding, but still it is quite invariant to the changes, right? This is again the other example. Now the problem with the Harris corner detector is it's not invariant to changes in the scale, right? So for example, here it's an edge, but we can clearly see that this location should be a corner. If you use the much bigger window size, or if the image was a bit scaled a little bit down, you could see clearly that this place should be a corner, but when you are zoomed in, the place becomes an edge. So definitely Harris corner detector is very, very much variant, is not invariant to changes in the scale. Now, again, as we said, there are other techniques to define the R. So there is the Shih-Tomasi corner detector, which is just a Harris corner detector, but with a small modification, where the modification shows better results compared to the Harris corner detector. And it's a very simple one. R is equal to the minimum between lambda 1 and lambda 2. If lambda 1 is very big and lambda 2 is also very big, then their minimum is very big. If lambda 1 and lambda 2 are very small, so their minimum is very small. So again, it's a flat region and we don't want it. If either one of them is small and the other is big, it means it's an edge and the minimum will be very small and we do not want that. So the minimum is a very good, R value to help us detect corners. It's better than this one and it's much faster to compute, definitely, than this one. So if it is greater than the thresholded value, then it is considered a corner. This is just an example of its results. We're not going to go deeper into it, but it's exactly the same thing as the Harris corner detector. Now we have the scale invariant feature transform. SIFT is just a small modification to Harris corner detector. It's something that you should easily understand, but it's much better in terms of results. And we will have another, after this one, we will just speak a little bit about how to build, yes, exactly, how to build these, what are they called? Feature descriptors and key point descriptors. And that would be it for the SIFT, right? So SIFT, again, just consider it as, for now, as a simple algorithm that is very similar to Harris corner detector, but a little bit more. So as you can see, scale invariant feature transform. So the scale invariant SIFT detector is very good for a feature detectoring and of course for describing the features too. So this could be used to do the feature image matchings as before, as we have seen before, right? So it is reasonably invariant to changes in illumination, image noise, rotation, but most importantly, scaling. And it is also invariant to small changes in the viewpoint. So for example, here you have this truck in this image. You have this same truck in another location. Again, it's not that different in terms of like the viewpoint. So we can still see the front, we can still see the top side, and we can still see the left side. But there is a little bit of a difference, right? So it's not exactly the same. It is definitely not the same scale. So this one is much bigger than this one in this image. It is not the same rotation. And there is no image noise, but definitely there is a little bit of illumination differences between the two, right? So here you can see that the back in here is very bright, whereas the back in here is not very bright. This one is like a professional photo taken, right? and this is just something in actual boxes, right, in real life. So you can see that there is a difference in illumination, there is a change in the viewpoint, there is a change in the scale and rotation, and still the SIFT feature detector and feature describer was able to do the extract features that are quite similar between the two of them, and that led to the ability to do this feature matching between them. And this was like in 1999, right? So it's quite old, guys. So these are the different stages for SIFT feature detector and describer, right? So the first stages are required for doing the detection of scale invariant features. And then the final stage would be just to describe those features. And it's a very simple way to describe them, similar to what we have seen in HOG, for example. So the first problem that we're facing with is that some of these corners, if you scale them up too much, you will get an edge. So this is the main issue that SIFT is trying to solve. Scale invariant detection is about finding the appropriate size. So previously, as we said, finding the appropriate window size for each image. So it should be something that we define for each different image. And we could be, for example, in this case, instead of using a smaller size for the window, we could use a window that is this big, and that would tell us that this point is a corner. If we use a smaller window, it will tell us that this point is a edge. So you could imagine that we're just going to apply basically the Harris corner detector, but at each pixel, we don't just use one window size, we use, let's say, 6 different window sizes, and they're very big on top of each other. And whichever one tells us there is a corner, we take that one, right? So we ignore anything that tells us this is an edge, this is an edge, this is an edge. We only take the one that tells us this is a corner. So how do we choose corresponding window sizes independently in each image? And do objects have characteristic scales that we can identify? So as we said, we will try to define some sort of a function in which we take just the maximum solution for it. So for example, before, as we said, we have just one window, and that window, it just tells us it's an edge. If we try to do that window and just make its size much bigger, just pixel by pixel. So for example, previously it was a 5 by 5 window. Now it's a 6 by 6, and then it's a 7 by 7, and then it's an 8 by 8, and then it's a 9 by 9. And we continue gradually increasing it. That would give us a function of the R, right? So let's say when we are like zoomed in, we are at an edge. And the R, again, is minimum between the two of them. So for the edge, we have this function. So it's a small, 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 small. And the bigger we get, the bigger the size of the window we get, the more we get closer to a corner. Imagine that we get too close to a corner, and then we just zoom out a lot, and that again becomes useless information because we're no longer actually capturing something that is useful. So this gives us the function of R while we change the size of the window. So this is not A, this is R. Yeah, so this is the function of R while we're changing the size of the window. A good function should look something like this, right? So a good function, let's go there here. So a good function should have just one place where it is a corner. So just one time, one scale. For that scale, it is a corner. Everything else, it should not be a corner. And it should not be like multiple different regions that could give us a corner. So it's not a corner at 6 pixels. And again, it's a corner at 20 pixels and 70 pixels, right? It should be a corner at just one scale, and that's it. And this, again, the same thing, right? So it's an edge, then you scale up, it becomes a corner, then you scale up a little bit again, and then it becomes an edge, and then you scale up again, and it becomes a corner, scale up. So it's a lot of work in here. So this is bad, this is bad, this is what we consider as a good scaling function. So the idea behind this is quite simple, or the trick behind it is quite simple. Instead of just using, so basically what we want to do is we want to calculate the, what is it called? The derivatives, but not for the same, not for just one window size, right? We want to calculate the derivatives for, let's say, 20 different window sizes. We can do that, but it will be very, very difficult to calculate all of that, to apply the Harris-Corder detector with 20 different window sizes. The trick could be to use Gaussian techniques, right? So Gaussian techniques, what they do is they will blur the image a little bit, and they will make that same window size, you have just one window size, right? That same window size could contain more information about the rest of the image than it would when you don't apply the Gaussian. So this is just a little bit reasoning why we have the Gaussian. We will see how do we use it a little bit forward. So we need to identify those locations and scales that are identifiable from different views of the same object. This can be efficiently achieved using a scale space function. A reasonable assumption, as we said, is that we will be using the Gaussian function because it will simplify a little bit the work for us. Instead of having to calculate for multiple different window sizes, or like for all the different window sizes, Gaussian function could just like merge, let's say, 4 different window sizes together, and that would reduce a little bit your calculations. So here, this is just a basic multiplication. This is the convolution operation. This is the variable scale Gaussian. So it depends on the sigma in here. And this is the input image. So the Laplacian of Gaussians is one such technique that can do both the, what is it called? The Gaussian and of course the calculation of the derivatives. But its calculation is quite costly, so the solution was to approximate the Laplacian of Gaussians. So the approximation of Laplacian of Gaussians is used through the approximation of the differences between the Gaussians, right? So the difference between the Gaussians is equal to Laplacian of Gaussian of xy at the location xy and k sigma. This is k is just a multiplier, minus L of xy and sigma, where L is already defined in here, right? So this gives us this following idea. So imagine that you have this pyramid of different scales. So this is the first window scales. So let's imagine that this is the scale of 5 by 5. You see they're all the same. And what we will be doing is we will calculate different Gaussians for all of these, right? So each scale, we will calculate different Gaussians, and that would simplify a little bit the work for us. And instead of going to calculate the Laplacian of Gaussian for each one of them, we just calculate the difference between 2 consecutive Gaussian functions of the image, right? And that would give us the following results. So images are, afterwards, what we get is the, So here what we get is the scale space generation, and that gives us 5 blur levels for each different octave. So here we have just the first octave with the first size, the second octave, the third, and the fourth. And the differences between the octaves are quite huge, right? So here we have, let's say, I don't know, 20 by 20, and here it's 10 by 10. But what if the thing that you're looking for is at like 19 by 19 or 18 by 18? So in order to do that, we use the Gaussian to blur a little bit the images, and that gives us the ability to kind of merge the results from the window size from 18 till window size 22. They will be kind of mushed together, and we're able to calculate it. But instead of calculating the, the derivative at each step, what we do is we calculate the difference between the different Gaussians. So what is a Gaussian, right? So for example, you have 1 pixel in here. If you don't use any Gaussian techniques, all these pixels will be the same, and their minuses would have no difference. But what happens when you have like a Gaussian is this pixel is going to be a combination, a linear combination of what is around it. And this pixel will be a different linear or a more spread out linear combination of what is around it. So if you do the minus, it's going to be similar to the Sobol filter of, you know, some sort of linear combination between the values of the pixels around that central point. So this is what approximates that idea of a derivative through just the difference of Gaussians, right? So instead of having to calculate the derivatives manually, now you're just calculating different Gaussians and you're doing the differences between them, which leads to basically having the idea of derivative calculation directly. So here we have, as we said, multiple octaves because we're going to be doing this at different scales. So for example, this one, as we said, is a very big window size. This one is a medium window size, and then we will do it for the smallest medium size. At each one of these sizes will be done at each type of pixel, right? So for each pixel, let's imagine that we will have, I don't know, we will have 20 different matrices. And for each one of these 20 different matrices, we will calculate its R. And here we will get an R that looks like this, right? So the R for each pixel would look something like this. Hopefully, this is what happens is for the big sizes, we don't see any corners. For the super small sizes, we also don't see any corners. But for the sizes in the middle, we see something. If it's the same pixel, but at a different scale, what happens should be like this. Right. So it's the same corner, but at different scales. What happens is we should be able to detect it if the scale is very big or if the scale is very small, because we will be applying the same technique at different scales. And basically what we'll be doing is we will be searching all of those different differences of Gaussians for a local extrema. So just that one point that makes it a perfect corner, right? So that one scale that makes it a perfect corner. So one pixel in an image is compared with its 8 neighbors, as well as its nice 9 pixels in the next scale and the 9 pixels in its previous scale. If it is a local extremum, it is potential key point. So this point is going to be compared to all of these points. If it is much bigger than all of them, then it could be potentially our corner that we're looking for. Sorry. And this gets us to this example of the application. So key point localization in here. Now we have so many less points than pixels. However, it is still a lot of pixels, right? So here we can see that it still contains a lot of pixels. Its results are quite similar to the Harris corner detector, because as you can see, it does not care about the edges. It only cares about places where there is a major change in all the directions, and how do we approximate that is basically a change in all the, what is it called? The Gaussian Gaussian estimations of that image. And that gives us basically the changes in all the directions. Key point localization. Now we're starting to work on the concept of comparing it a little bit to the Harris corner detector. So SIFT also used the Taylor series expansion of scale space to get more accurate location of extremums. If the intensity at extremum is smaller than the assigned value at it, then we just reject it. So it's a flat region that does not have a lot of changes in it. What is it? Difference of Gaussian has higher response values for edges, which is very similar to the Harris corner, not as similar to the Harris corner detector, but more similar to the Laplacian of Gaussians, which we have seen in the second or third lecture. So it's not perfect for us. So instead of using just Laplacian of Gaussian as something that we would like to aim for, now we're trying to use the Hessian matrix H to compute basically the principal curvature, right? So something that is able to find corners much more likely able to find the corners than it is likely to find the edges, as we have seen in this example. We know from Harris corner detector for the edges, one eigenvalue is much larger than the other. So basically, if this ratio is greater than the threshold, that key point is discarded. So what happens is we have the points that are proposed by SIFT. We calculate the R. If the R is smaller than a certain threshold, then we just don't calculate it. In this case, the R is defined as a what is it called? As a division. So division between lambda1 and lambda2, but you can define it as a minimum. You can define it as a big function of lambda1, lambda2 minus alpha of lambda1 plus lambda2 squared. It's up to you. After the localization, we have the stable key points, and now we want to describe these stable key points, right? So an orientation is assigned at each key point. So this is the key point that we're interested in. For example, this point, right? It has its neighborhood. A neighborhood is taken around the key point location depending on the scale of that key point. So again, the key point is detected at a certain difference of Gaussians, right? So it depends on its scale. It will have a different size at each different scales. And the gradient magnitude and direction is calculated in that region. Again, very similar to how we did in histogram of oriented gradients. We will calculate an orientation histogram with 36 bins covering 360 degrees. Unlike, I think, in histogram of oriented gradients, we were working from 0 to 180. Here we have all the possible degrees that we can ask for. And here we have the histogram that defines basically this one, that defines exactly this beautiful stable key point, or this specific point of interest that we're looking for to describe. So the key point descriptor will just merge all of these. So at this point, each key point has a location, scale, and orientation. Now what we can compute is a descriptor, or like the big description for each local image region about each key point. So we can compute a descriptor for the local image region. So for that, for this region that we zoomed into, we can compute its local image region key point feature descriptor. How do you say this? For each key point, we can have a different descriptor, basically, right? So this descriptor would have a information about its scale, its location, and of course, it's basically the changes in the gradients happening around it, right? So what are their orientation, and what is the intensity of those pixels, or of the, what are they called? The gradients that are near it, right? So it's again very similar to what we did with HOG, but now it's more region size instead of image sized, right? So based on a 16 by 16 batch, we define a 4 by 4 subregions. 8 bins in each subregion will be calculated, and that would give us 128 dimensions in total to describe that image, right? So that describes basically that key point with 128 dimensions. 128 is definitely big, right? So it's not a very small, what is it called? It's not a small vector. So here, for example, we can do the math. So this is the image of 233 pixels by 189. We will detect a lot of interest points. After doing some thresholding, we would get to like 536, but still 536 is a lot of different points, especially when you take into account how many different, how much the dimensions of each key point will be, right? So the description of each key point will be quite large. So SIFT is quite robust when it comes to, as we said, changes in the viewpoint, changes in illumination, and changes in the scale, especially. That's like the main thing that it works on. And it's fast and efficient, but it's not perfect, right? So here you can find lots of different versions of SIFT that can approximate things a little bit better and that would give you much better results. And the final thing, once we have these different features, right, we have the key points that are interesting regardless of their scale. We have the information on what's happening in there that is scale dependent, right? So we don't have just like a group of pixels that are surrounding that specific, what is it called? That specific key point, right? Now we have a group of like an information vector for that specific key point at the perfect scale for it, right? So if you have an image, not like this, not like this. Yeah, if you have an image like this, for example, right? So you have an image in here and an image, it's the same image here. What happens is this pixel, for example, we said that this pixel is an interesting pixel. Its window size was like 10 by 10. In here, its window size or its descriptor would be much smaller in window size, like its region of interest that we're using to calculate its feature descriptor would be much smaller, and making the 128, how much is, just to confirm the size? Yeah, the 128 feature descriptor very similar between the two images, even though the sizes are very different. So the scales of the images are very different. So now let's go back to basically the final step, which is feature matching between different images at different scales and different illuminations and different etc. Right? So which features match? So here, for example, we have, this is the, if I'm not mistaken, in Milan, like the, no, this is not in Milan. This is, what is this? I have no idea what this is. So this is some sort of cathedral. I'm not sure where it is. Looks a bit French. It's European. So here what it does is we will use SIFT to detect points of interest. So for example, you can see here, these 2 points were detected at this image, and they were detected also at this image. This point was detected at this image, was detected at this image. So it's the same place, right? Again, same place, same place, same place, same place. And this is the beauty of using the SIFT feature describer, right? So, or feature detector and feature describer. It usually finds the same features in different images, but for example, for this one, it managed to find only one of these 2 points, right? Although they're like quite similar, it did not find that point as a corner or as a feature of interest any longer. But the majority of them are the same. So you see this one, perfect match, this one, perfect match. For example, this pixel, it does not exist in here, mainly because of this tree. And this, I think there's some working happening here, construction. The door, of course, is hidden, so we can't do the matching in this region. And there are some extremely harder cases where SIFT is going to have to, you know, be pushed to its limits. So for example, here you have the image of, I don't know, this is probably like the moon or something. And this is a much more zoomed in version because somebody is walking on the moon and you would like to understand basically what's happening, right? Where are you? Oh, outside, and where are you inside? This and this is going to be very difficult to match, right? So you don't have like the object in the center. So the points of interest that you're looking for are not in the center. They're like at the extremum locations of the image. That's a bit difficult to match. But for the feature matching technique, it's going to be a basic technique, right? So it's very similar to if you have seen KNN. I'm sure you have seen it with Professor Khan, but it's very similar concept to basically KNN, right? So the feature matching, you have lots of features on one side and lots of features on the other side. Each one of them has like a vector of 128 features that could be used to basically match each other. So what we do is we compute basically the L2 distance between each different, each two different, what are they called? Features from image 1 and image 2. And basically we just match them based on that, right? If they have a very small distance, then that's good, or the smallest distance, that's the good thing for us. If it's not, then we don't take it. How to discard the bad matches? Thresholding on L2 is gives us some bad performance, right? Because some images, for example, here, I don't know, this feature from image 1 and this feature in image 2, this feature could be very similar to this one, but also could be very similar to this one, right? And the actual value that is similar to this should probably be this one. But for some reason, our feature detectors in the two images gave us this is the smallest link. So this would ruin a little bit our performance. In order to solve this, they created like a very small trick, which is the thresholding on a ratio. So instead of thresholding based on the closest match, the smallest distance, we are now thresholding based on the ratio between the smallest match and the second smallest match. So the second closest match may be very near to the first one. And if that's the case, in this case, the ratio of closest distance to second closest distance is taken. So this one is like, so these cases or these scenarios will be more similar. We will see them in this example, right? So in this example, for example, you can see that all of these are extremely similar. And the idea of using just the distance or the L2 distance clearly breaks in such scenarios. But the idea of using the ratio will definitely help us. So here, given a feature in I1 or image 1, how to find the best match in image 2? You first define the distance function that compares the two descriptors, test all the features in I2, and then find the one with the minimum distance. So here what we can do is how to define the difference between the two features. Simple approach, L2 distance, F1 minus F2. It can give small differences for ambiguous incorrect matches. So F1 and F2, for example, they're not the correct match. We want this to be matched with this one. And that leads to a very high error rate. The better approach is to find the ratio of distance between F1, F2, and F1 and F star 2. F star 2 is basically the second best match that we have, right? So F2 is the best match F2 is the best match to F1 in image 2, and F2 hat or whatever this is the second best match to F1 in I2. This gives us like this distance function is like gives us larger values for ambiguous matches, and that could help us like reduce basically the what is it called, the false positives, or the false positives. I hope we will see. Feature matching example. So this is a what is it called, like an image, and here it is the same image. It's a little bit different. For example, this BBC, you see, we don't have it in here. This one also, we don't have it in here, but the majority of things are shared between the two images. And even though the scale is very different, here it's colored, here it's not colored, so the intensities are like even more different. You can see that this place is a bit dark because of basically it's not well illuminated, whereas this one is extremely well illuminated, and still SIFT was able to detect this and some of these faces in here. So here, for example, how can we measure the performance of a feature matcher? So this is based on the feature distance. This, for example, I think this is like in, what is it called? In Rome, like the fountain thing. And they have this, the head of this, what is this called? Statue. We were able to match it directly to this head. This location was able to be matched to this location, but for some reason, it said that the legs of this statue are very, very similar to the head of this thing in here, which is not very correct, right? Oh, sorry. Yeah, so these are like true matches, and this is a false match. So measuring the, basically measuring the performance of a feature matcher we need to, like, we can think of it as just a classification problem, right? So what we can do is we measure the distance between, the distance threshold affects basically the performance. So if you use the distance threshold, set it to 80, then this would be a very good model. But if you set it to 250, then it's not a very, very good model. The true positives is equal to, just to like the small definition, true positives is equal to the number of those which were detected matches that are correct. We want to maximize these, and the false positives means that they were detected as a match, but they are not a match. So meaning the number of detected matches that are not correct. And we want to minimize these. So here we have this beautiful, what is it called? Chart that puts recall on one side and 1 minus specificity on the other side. So the true positive rate simply means the number of true positives divided by all of those that were predicted as positives. So here the number of all matching features that are positives. So this is the true positive rate. And the false positive rate is the number of false positives divided by the number of unmatched features. So basically the negatives. And this gives us 1 minus the specificity versus the recall on the other side. Sorry. And this, you have the ROC curve, or receiver operator characteristic curve. It's quite similar to basically the recall precision recall curve, right? That one. And it gives us basically one value or one number that can tell us how good our model is performing. And that number is, again, the area under the curve, very similarly, as we said, to the precision recall curve. And it gives us the AOC, for example, here, it's 0.78. If we were perfect, that means for any threshold we will use, we should get something very close to this, right? That stays within. And that means that the model is absolutely perfect for any threshold that you use. It's perfect, but that's not always the case. So for example, if you use a very, very small or very, very large threshold, you would have a large amount of, very small amount of recall and a very small amount of 1 minus the specificity, which is good. But here, if you use a very large threshold, you will have a much higher recall, but also a much higher false positive rate, which is something that we don't want. So the application areas are quite, as we said, quite limitless. So for example, we have image alignment, 3D reconstruction, motion tracking, object recognition, indexing, robot navigation, and etc. So the applications of this technique are limitless, right? And we have seen for today are the following. So we've seen different feature detectors. Namely, we have seen the Harris detector, and we've seen how to change a little bit the R function to get us the Shay-Tomsky detector, which is even better than the Harris detector and much simpler than it. And we've seen the low detector, or the SIFT detector, basically, which is very similar to the Harris detector, but it works at a much better results for, gives much better results for different scaled functions, right? So for example, if the image is, I don't know, scaled 4 or 5 times, you can still find the same features, or at least the majority of the same features between that image and the other image that was scaled 5 times. The feature descriptor from SIFT is very similar to what we have seen in HOG. So that allows us to build a feature descriptor for specific regions at specific scales. that would be similar to the other regions in the other scale. So if you have an image like this, and you have a bigger image like this, but the part that you're matching is here. So this one is 200 by 200, let's say, and this one is 50 by 50. Using SIFT, you can find the same interest points, and even better, you can describe them in very similar manners, even though they are at different scales, right? So if you used like a very basic model that just looks at it in here with a 5 by 5 location and tries to build the hog for it, and here it's a 5 by 5 location and tries to build the hog for it, the two different descriptors would be very, very different. But with SIFT, we have the ability to build a feature descriptor at the perfect, or what we consider as the perfect scale. Hence, it will be very much, what is it called? Similar between the two different images, regardless of their scales. And then, of course, the last part, we've seen how to do feature matching based on the L2 distance, which is extremely similar to the concept of the, what is it called? The concept of KNN, basically. And that would be it for today's lecture. I think we still have some time, right? Just a couple of few minutes. As I said, hopefully for next week, we're going to have the first midterm. The midterm is going to be very simple, and it's going to be, I think, 45 minutes. It should be quite fast, right? It's a very simple QCM on Moodle, where you basically just answer the questions, just choose the correct answer from these questions. The content that will be covered will be everything before today's lecture. So basically lecture 1, 2, 3, and 4, I think, right? Yeah, lecture 1, 2, 3, and 4. And lecture 5 is not going to be included. There will not be a lot of questions from the lab, I think. So the lab participation will be like measured in the lab, but this one will be just about the theoretical concept. It should be very simple to do. It will be in presence, so you will have to go to the university during the lecture time, and basically we will set up some room where you all be in the same place and open your laptop and basically do the midterm, right? And Batul will be there to watch you guys, so no cheating. Do you guys have any questions about the lecture or about the midterm or about the project? Because the project is also going to be out today.
So when will be the deadline for submitting the project report?
The project ideas deadline will be in a week. It's just a week, right? It's just the idea. So basically just tell me the idea. That's it.
Okay, thank you.
And the project's results, the first project's results will be measured 4 weeks after that. So 4 weeks after that, I would need to see some code, some examples, something moving a little bit, and some, I don't know, some structure for your report. And then, of course, 4 weeks after those 4 weeks, we will have the basically project defense, right? So you just present your projects. All good?
Yeah.
Perfect. So good luck, guys. I think you're going to be a little bit late for Batul. So see you next week. Again, good luck for your midterms.
Thank you. Goodbye.
Bye-bye.